Hi everyone, myself Dr. S. Kannappan. I present the course Digital Signal Processing. This is Module 4, Design of IIR Filters. So in previous modules, we covered in Module 1 the basics of digital signal processing and discrete time signals on system. And in Module 2, we covered the important Fourier transform in digital signal processing, that is discrete Fourier transform, and also Z transform. In module 3, we discussed about an efficient method of calculating DFT, that is fast Fourier transform. So with this, the signal analysis in frequency domain is completely discussed. Now let us move on to the design of filters. So filters are very crucial in many signal processing applications. We have seen some at the beginning of the course. In module 1 we have seen some of the applications of DSP, like ECG signal processing, and in EEG applications, and many applications like hearing aids. So every device requires a filter of the unwanted signals. So here the system we are considering as a digital system, we are considering IIR filter and FIR filters. So filters can be classified in many ways. So in digital, one of the classification is based on the impulse response. If the impulse response is infinite number of samples, then it is called IIR filter. If the impulse response of the filter contains finite number of samples, then it is FIR filter. So module 4 and module 5 is particularly to discuss about these two types of filters design. Now, before going to discuss about the design of IIR filters, let us see some basic difference between IIR and FIR filter. So IIR filter means, as we said, the definition itself conveys infinite number of impulses. That is, impulse response is infinite duration in IIR, but whereas in FIR the impulse response is finite. And IIR is a recursive system. IIR filters are recursive filters, but FIR is not recursive filter. That means there is no feedback in IIR. In FIR, there is no feedback, but in IIR there is a feedback. That's why it is called recursive filter. FIR is non-recursive filter. And phase response, you see, for any system phase response is very much important. Hence the phase response of any system must be linear. If it has linear phase response, means the phase is changing linearly with respect to frequency. Then if the frequency increases its linear relation with frequency, the phase also varies linearly. So whereas if you consider IIR versus FIR, the phase response in IIR filter is non-linear, but in FIR it can get exactly linear phase response. So it's a most advantage of FIR filter over IIR. And the order of the filter. So for designing any given specification for any filter, IIR needs very low order. With a less order, it can able to achieve that specification, but FIR needs higher order to achieve the any specification. And the important thing, another important thing is stability. The stability of IIR filter has to be decided based on the poles, but FIR filter is always stable. So the stability of the FIR filter is very high. So, and some design methods we want to follow to design any required filter by using some kind of methods. So in FIR, we have some kind of methods called windowing techniques and frequency sampling technique. These are all some techniques. Directly we can design a digital filter, but in IIR we cannot design the digital filter directly. We have to design analog and then it has to be converted into digital, because the impulse response is infinite number of impulses. As it is infinite number of impulses, we cannot store those impulses, infinite number of samples, in a register or in the digital device. Hence, first we will approximate the analog prototype for getting infinite number of impulses, and that analog transfer function is converted into digital. So this is the method we are going to follow in IIR field. Whereas in FIR, we'll use windowing technique, such that we'll discuss what is windowing technique, why we want to go for windowing technique. That we'll discuss in the FIR field. And as I told, the applications of filters, it has a lot of applications like audio applications and analog like applications for IAR. But for FIR, it has a lot of medical imaging and image processing applications, communications, and so. Now let us move into IAR filter design. As we have discussed, IAR filter cannot be discussed directly in digital domain. We want to design in analog first, and then it has to be converted into digital. So we have two types of analog prototype for IAR. So that is Butterworth and Chebyshev. So we can design any type of frequency selective filter, either it is low pass filter, high pass filter, band pass filter, or band stop filter, either Butterworth type or Chebyshev type filter. Now, before going to discuss about these two types of filters, Butterworth and Chebyshev, let us discuss about some classification of the filters, basic classification of the filters, that is frequency selective filters. Based on the frequency interest, we can divide it into some types of basic types we know. And main importantly, we want to see about these frequency selective filters in two scenarios. One is ideal filter and another one is practical filter, because we are going to design the filter practically. So how the frequency response of the filter will be changed with respect to frequency in practical manner. So, but ideally, we know the ideal filter, how it must be. But practically, it is not possible to achieve that ideal transfer function. So let us see that first, and then we'll come into the Butterworth low pass filter, and then it is converted into any high pass, band pass, or band stop. Similarly, Chebyshev low pass filter will design, it can be converted into any other type of. Now let's see here low pass filter. So we have four types of classification in the frequency selective filters. So first of all, let's recap all the basics, like what is filter. So the filter means a system which will allow a required band of frequency in the input to the output, and it will avoid the unwanted frequencies in the input signal uh, that is restricted to uh, pass on to the output. That's a filter. Filter is a system, just it will pass the required frequencies from input to output, or it can restrict the unwanted frequencies from input to output. So these filters, so here the frequency is the main important uh, measuring parameter. So it is called frequency selective filters. So the frequency selective filters are of four types. One is low pass filter, high pass filter, band pass filter, and band stop. You see, let's see the low pass filter characteristics. What is low pass filter? The filter that allows the input signal up to some cutoff frequency. From 0 to cutoff frequency, it will allow the input signal, and it will completely eliminate the signals which are having frequencies more than the cutoff frequency. That means, so some low frequency signals only it will pass to the output. The high frequency signals are restricted to allow to the output. So this is a transfer function. So h of e power j omega or h of j omega is equal to 1 in up to omega c, and it is 0 greater than omega c. So where the transfer function is 1 is called pass band, where the transfer function is 0 is called the stop band. So transfer function means we know output by input, transform of output by transform of input. The transform of output by transform of input equal to 1 means output is equal to input. That means input will be passed, hence it is called pass band, and it is 0 means output is equal to 0, as it is completely stopping the input signal to reach to the output. So it is stop band. So this mathematically we can represent as h of e power j omega magnitude is equal to 1 for omega less than or equal to omega c. It is 0 for omega greater than omega c. But ideally it is possible to switch at a sharp frequency from high to low. That is 1 to 0. The transfer function can be sharply changed at omega c. But practically, if you design a filter, it cannot achieve this sharp transition from pass band to stop band. It cannot be possible. So practically, it needs some time to change from pass band to stop band. Slowly, gradually, it will decrease to 0. The betterment of this filter depends on how fastly it is changing from high to 0. So this transition band should be as less as possible. If the transition band is less, then it will approach to ideality transfer function. If the transfer function has more transition band, it is deviating from the ideal transfer function. Hence it is slowly changing. We need to locate two frequencies. There is no sharp cutoff frequency omega c. We have two cutoff frequencies, pass band frequency and stop band, apart from the cutoff frequency. Then what is the acceptable frequency can be considered as a cutoff frequency, means the 3 dB frequency is the acceptable frequency as a cutoff frequency. So 3 dB frequency means, so one, if it consider this magnitude is plot is converted into logarithmic plot. So log 1 is 0 and the value less than 1 means it is negative decibels. Log 1 is 0. If it is decreasing means towards 0 means less than 1. So it is minus 3 dB, minus 1 dB, minus 2 dB, minus 3 dB, and so on. It is increasing to infinite decibels. The transfer function having minus 3 dB at a particular frequency, that frequency is considered as omega c. What is 3 dB means in magnitude plot is 1 by root 2 level is equivalent to minus 3 dB in the decibel scale. So 1 by root 2 means 0.707. That means 70% of 1. So the 70% of maximum value. That means we can consider a pass band. Pass band means the input signal can be allowed to the output only up to 3 dB frequency. That means the magnitude of the input signal can be 70% of the maximum input signal. If it is 1, the input signal will be as it is, will be transferred to output, but it is decreasing. So how much we can acceptable range means 70% of the input signal, 0.707, 70.7%. So if it is less than the, so if it is 50%, if it is more than 3 dB means maybe 50% or 40% or 30%. So 40% of the signal is means we cannot recognize the signal at the output end. That's why we have to consider omega c as 3 dB frequency. And for my application, not I don't want to compromise up to 70% of input signal. I need more percentage of input signal to be reproduced at the output. That means I can reduce the passband frequency which is having less than minus 3 dB. That is, I can consider minus 1 dB only to be the deviation from 0 dB. At that, the frequency at which we have minus 1 dB can be considered as omega. That depends on our application. If my application require less deviation from the actual input, means we need to fix some other frequency as a passband frequency. And similarly, stop band frequency. Stop band frequency means generally cutoff frequency is above the cutoff frequency we will consider as stop band. But I don't want to take 50% of the input signal should be appear at the output during this stop band frequency. I want completely, I can allow up to some 5%. So 5% of input signal can be considered as like a stop band frequency. So that is a minimum input signal that can be considered as a zero signal. That is, I have to fix some other frequency other than the minus 3 dB. I want to fix some minus 30 dB. Minus 30 dB means more deviation from 0 dB. Means from 1, it is very deviating from 1 towards 0. So we can fix two frequencies other than the omega frequency, omega c, in the practical filters, because the practical is not sharply changing from passband frequency to stop band. So as it is decaying gradually, we depends on the requirement, we want to choose some other frequencies as passband frequency and stop band frequency than the cutoff frequency, right? So omega p is passband frequency, omega s is stop band frequency, omega c is cutoff frequency at minus 3 dB. And the deviation from maximum value at omega p is called attenuation, passband attenuation, so alpha p. So this much of attenuation can be acceptable in the passband. That is called maximum allowable variation in the passband. So this is passband ripple. We can say it is passband ripple. It is in decibels. And alpha s is stop band ripple. This is the minimum attenuation that can be fixed at the stop band. It may be more than that also. So minimum we need this one, but it may be more than this deviation. Deviation can be more. Deviation is some maximum towards origin. The deviation can be very high. So the transfer function looks like this. So alpha s is stop band ripple, stop band attenuation in decibels. Alpha p is passband attenuation or passband ripple. So similarly, we can see for high pass filter. High pass filter also same. First we will get the stop band, next we will get the pass band. Here also we can locate omega C, omega S, and omega P. So in high pass, omega S is less than the omega P. So first we will get stop band, next we will get pass band. Just now let's see the band pass filter. The band pass filter, similarly, it has stop band and pass band, but in band pass filter, the some band of frequency is allowed, and remaining except the band of frequency, remaining frequencies are restricted. It is not up to the some cutoff frequency or from the cutoff frequency. It is between the two cutoff frequencies. So this cutoff frequencies are represented with lower cutoff frequency and upper cutoff frequency. Between lower cutoff frequency and upper cutoff frequency, the frequency signals can be transferred to output. So here also same. Here we'll get two stop bands and one pass band. This from stop band to pass band, it cannot change sharply. It has to go gradually. Similarly, from pass band to stop band, it will decrease gradually. Hence, so we'll consider the pass band where two frequencies we have to consider for lower pass band frequency and upper pass band. Similarly, stop band, we have two stop band frequencies, lower stop band frequency and upper stop band frequency. So omega 1, omega 2 are indicate stop band frequencies, but omega L and omega U indicates the pass band frequency. So in the same way, band stop filter. So band stop filter means it will reject the particular band of frequencies and it will allow the remaining all frequencies. So it has two cutoff frequencies, lower cutoff frequency and upper cutoff frequency, but it is stop band frequency. So omega 1 and omega 2 are the two stop band frequencies. And pass band frequency, pass band to stop band, it is changing at the beginning, and again from stop band to pass band it is changing. So lower pass band frequency means from when it is changing from pass band to stop band, that pass band frequency is lower pass band. It is changing from stop band to pass band, that pass band edge is upper pass band edge. So this is practical transfer function character. So whenever if they want to design a practical filter, they need some specification. That specification is nothing but these frequencies. So this cutoff frequencies and pass band frequency, stop band frequency, and the variation from, that means ripples, or we can say attenuation in the pass band and stop band. So this, I want this much of attenuation, I want more attenuations, I want less attenuation. I want the pass band frequencies should be less than 1000 Hz, or it should be at 1000 Hz, or maybe 1500 Hz, just like that. So we can choose it based on our application. So the user will give the specification, and the designer will design the particular transfer function for attaining that specification. Now let us see. Now we'll go into the low pass filter design by using Butterworth filter transfer. So we have two types of analog filters, Butterworth and Chebyshev. So let us see this Butterworth filter. The Butterworth filter transfer function is, this is the transfer function for Butterworth. Mod h of e power j omega is equal to, or h of s, we can say s is nothing but sigma plus j omega. Sigma will consider at a particular value, so omega is changing, so h of j omega can be, or we can represent it as h of s also. The transfer function, general transfer function is for a low pass filter, Butterworth transfer function is modulus of h of j omega is equal to 1 by square root of 1 plus omega by omega c whole power 2n. Here n indicates the order of the filter. If the order of the filter increases, then it will give a better results. band transfer function curve. That means it approaches the ideal curve. When n is less, it deviates from the ideal curve. What is the ideal curve for low pass filter? We know it is sharp edge from pass band to stop band. So you can see this multiple transfer functions within this graph. When n is equal to 1, it is gradually decreasing from pass band to stop band. But n is equal to 2, it's better than the gradual, very slow. It is fastly decreasing than the n is equal to 1. Similarly, to take n is equal to 5, it is almost similar to the ideal transfer. So it is approaching high, completely high, and it is approaching to 0 in a sharp duration, that is very less transition. So what is order indicates actually? The order indicates the number of poles in the transfer function. This is the transfer function 1 by 1 plus omega. J omega is actually s, so it is denominator is having s, so the roots of the denominator is poles. So if the denominator polynomial has the order s, maximum power of the denominator polynomial indicates the order of the filter. That means if it is having s square, the maximum power in denominator, then it must have two poles. If it is having s power 3 is the maximum degree in the polynomial in the denominator, means it may contain three poles. So the order indicates the number of poles of the transfer function. And also, to achieve that n number of poles, so we need n number of storage elements physically in the system. So the order also indicates the number of storage elements in the system, like capacitors and inductors used in the system. As we are discussing about analog transfer function, so this analog transfer function is achieved by using this analog components. So that is the order. Hence, to achieve a better transfer function, we want to use more number of components. So that it will be possible to achieve the ideal transfer. The more the order we want to design, so more complexity will be included in the system. Now, designing means what? Design means first we want to calculate how many number of components we need, how many poles we need. That is the order of the filter we want to calculate. First we should know the order of the filter of the given specification, and then after finding the order, we'll just find out the pole locations. So if you know the pole locations, we can find the denominator polynomial. So the first part in the design is finding the order of the filter, and the second part is finding the poles, and hence calculating the transfer function for the. So as we have already discussed, this is the low pass filter practical transfer function. It is high at 0 dB, 0 frequency, and gradually it is decreasing towards 0. So at some frequency other than omega c, less than omega c, will consider some frequency as a pass band, because at that frequency the deviation is not minus 3 dB, it is less than greater than minus 3 dB or less than 3 dB. So somewhere it is 1 dB or 0.5 dB we want. More number of accuracy is required, more lot of accuracy is required, then we can say the pass band frequency must be less than the cutoff frequency. And similarly, stop band frequency will achieve more than the cutoff frequency, generally in the low pass filter. Right? So the two frequencies they will give in the specification, and at two frequencies they will give the pass band ripple and stop band ripple. How much deviation it has at the pass band frequency and stop band frequency, that is indicated with alpha p and alpha s in decibels. Now the order of the filter is calculated by simple derivation. Just we will apply omega equal to omega p and omega equal to omega s. Two frequencies will apply. So before that, just we'll apply a logarithmic. So because we want to find the order in in this formula, it is in uh, power of something. It is in power. So to get back that power, we want to apply the logarithmic for the entire equation. When you apply the logarithm and if you simplify it, 20 log h of equals. So 20 log h of e power j omega is nothing but the decibel value of h of e power j. So as it is decibel value at omega equal to omega p is minus alpha p, and at omega equal to omega s it is minus alpha s. Just if you substitute omega equal to omega p, this is alpha p, omega p will get cancelled. 1 whole power 2n is equal to just 1. So from this we will calculate epsilon is some constant. What is this epsilon constant? So this epsilon is equal to 1 generally at omega equal to omega c. At omega p, this denominator term is when it becomes omega c, then epsilon is equal to 1. So assume omega equal to omega c and denominator is omega c. So omega c will get cancelled, it is 1 by square root of epsilon square. So when omega equal to omega c, what is the value? 1 by root 2. The magnitude is 1 by root 2. When we will get 1 by root 2? When this is omega c get cancelled, and when epsilon becomes 1, then only it is 2. 1 by root 2 we can able to get. Hence, so epsilon is nothing but some constant that indicates whether we are in the pass band or we are in the stop. When epsilon is equal to 1 and less than 1, it is in the pass band. When it is more than 1, it is in the stop band. So just we calculated when omega equal to omega p, we'll get this constant formula. What is that constant? Epsilon is equal to square root of 10 power 0.1 alpha p minus 1. We know alpha p. Alpha p is nothing but pass band. Similarly, we'll calculate at omega equal to omega s. When we substitute omega equal to omega s by omega p will get, the term is separated because the term is having the n in the power. So that is separated and we'll extract the n by applying a logarithm on both sides. We'll get the final formula for the order. N is equal to logarithm square root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 by log omega s by omega p. So if you see all the terms in this formula is either omega p or omega s, it is pass band frequency or stop band frequency, and then alpha p and alpha s. So alpha p, alpha s are just the pass band attenuations or pass band ripple. Right. So order of the filter is n is greater than or equal to logarithm of square root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha by logarithm of omega s by omega. So n is always an integer and it is positive. The order indicates number of poles. Number of poles will never be negative. So it may be 0 or positive. That's why n is always positive and it may be 0. So 0 means there is no system. And n is greater than or equal to, why we are using this greater than or equal to means, as it is integer, if we get any fraction value, it has to be round off it to the next integer. That's why it is indicated with n greater than or equal to. Right? This is the order of the field. After finding the order, just we'll calculate the poles of the transfer function. The poles of the transfer function can be calculated as e power minus j pi k. So because the poles of the Butterworth transfer function lies on a circle. So circle means e power j pi k. So pi k is changing. K varies from 1 to n. N poles are there. So n poles related to phase we will calculate. So we can find that e power, this is the pole location is equal to e power j pi k. What is pi k means? Pi by 2 plus 2k minus 1 into pi by 2m. So just we can remember and we can substitute the values of k, and we can find uh, by using the n value, because n value already we have calculated. So instead of finding the poles, after finding the poles, we want to find out the denominator polynomial. What is the denominator polynomial? Means s minus s1 into s minus s2 up to and so on s minus sn. If we have n poles, then we have to product all the poles and we have to form the transfer. So instead of it, we can also find the transfer function based on the order. The order is even, and we can get one type of transfer function. If n is odd, we can get one type of transfer. So if you see, when n is odd, when n is odd, then the transfer function is omega c power n by s plus omega c. When n is odd, one pole must be at omega c, then s is equal to minus omega c. The remaining all are some other location, but we can represent as a product of second order polynomials at the denominator. So HA of s is equal to omega c power n by s plus omega c pi k is equal to 1 to n minus 1 by 2 s square plus bk omega c s plus omega c square. So omega c is cutoff frequency, and they will give. If they have not give, we have to find out the 3 dB frequency. So bk is a constant that can be calculated by using the formula 2 sine 2k minus 1 into pi by 2n, where k varies from 1 to n by 2 minus 1. And cutoff frequency, in some applications they may ask to find out the cutoff frequency. If you don't know cutoff frequency, we can take 3 dB, but otherwise they will give some other cutoff frequency also to design the filter. So we can find the cutoff frequency from the transfer function. So when already we discussed epsilon is equal to 1, that means omega equal to omega c. Or so just we'll substitute, then we can get the small manipulation with this one. Omega c equal to omega p into 1 by square root of 10 power 0.1 alpha p minus 1 whole power 1 by n, or square root, or we can find the what we can say whole power 1 by n value. So this is the formula for omega c. Either we can use omega p for finding omega c, or we can use omega s also. If it is omega p, the another term is 1 by square root of 10 power 0.1 alpha p minus 1. But if it is omega s, then omega c is equal to omega s into 1 by square root of 10 power 0.1 alpha s minus 1. Just now, so now let us see the design of an analog Butterworth transfer, Laplace transfer. So finally, we have to find out two things. One is order of the filter by using the formula, and second thing is we want to find out transfer function simply by using the formula omega c power n by sigma, instead of sigma pi, product of second order transfer functions. Second order transfer function has a uh, standard format. There is s square plus bk omega c s plus omega c square. When it is odd, apart from this second order polynomial, we have a single order polynomial also, that is s plus omega c. So if you see one problem, if you take similarly, they have given the specification. So from the specification, we can find out the pass band ripple and stop band ripple, and then pass band frequency, stop band frequency, and we'll substitute in the order formula. We'll calculate the order. N is equal to 3, it is odd. So odd means we have to use this formula omega c power n by s plus omega c into pi of second order transfer. So just we'll substitute and we'll calculate it. If the omega c is not given, we'll calculate omega c. If omega c is not given and a 3 dB frequency is given, then that frequency can be considered as omega c. As they have not mentioned, we can calculate omega c by using the formula. So now let's see the design of high pass filter and band pass filter and band stop filter um, by using Butterworth. Right? So we need some kind of frequency transformation. So basically, we'll calculate the low pass filter, and then that can be converted into high pass filter. But this procedure is same. Frequency transformation is same for any type of filters. So let us complete the Chebyshev filter also, and we'll complete the low pass filter design of Chebyshev filter, and then we'll move on to the design of any filter, either it is Butterworth low pass filter or Chebyshev low pass filter into high pass filter or band pass filter or band stop filter by simply applying the frequency transformation. So Chebyshev filter. So second type of filter is Chebyshev filter. So the Chebyshev filter is again classified into two types: type 1 Chebyshev filter and type 2 Chebyshev filter. In type 1, it has a ripple, equi-ripple or oscillations in the pass band, but in the stop band there is no oscillations. In type 2, the pass band is having no oscillations, but stop band is having oscillations. So based on the oscillations that is occurring in pass band or stop band, it is classified into type 1 and type 2. And the rest of the remaining characteristics are same. We have to locate pass band frequency and stop band frequency, and also cutoff frequency, pass band ripple and stop band ripple. Okay? So the design of type 1 Chebyshev filter. So here the standard transfer function, previously if we consider 1 by square root of 1 plus epsilon square into omega by omega p whole power 2. But here this transfer function is calculated by using a Chebyshev polynomial. So that Chebyshev polynomial is represented with Cn of x, which is a recursive polynomial case. So the Chebyshev filter is represented with mod h of j omega whole square is equal to 1 by 1 plus epsilon square into Cn square of omega by omega p. So what is Cn of x? So it is a polynomial. This polynomial is a cosine function or hyperbolic function. So cos of n cos inverse of x when frequency is less than cutoff frequency, or x is less than omega p. So here what is x here means this term Cn of x, omega by omega p is x, and omega by omega p is less than 1 means omega less than omega p. When omega is less than omega p, it is pass band. When omega is greater than omega p, it is stop band, because we are discussing the low pass filter. In low pass filter, we will get pass band first, next we will get the stop band. In the pass band, this Cn of x is indicated with cos of n cos inverse x. But in the stop band, Cn of x is represented with cos h of n cos h inverse x. The Chebyshev polynomial is also defined by using a recursive relation. So this can be used to find the different kind of values for the by using the recursive formula. So it's okay. So it's different values is there. Now we want to find out the order of the filter. So the same way as we have done in the Butterworth filter, just we have to apply the logarithm just to get back this n term. Okay? So to find the n value. So when you apply the logarithm and we'll substitute omega equal to omega p, we'll get alpha p at 20 log h of j omega. And so by that we'll get epsilon values square root of 10 power 0.1 alpha p minus 1. So previously also same formula we got for epsilon. Now if we substitute omega equal to omega s, then we'll get omega s by omega p. For a low pass filter, omega is always greater than omega p. Therefore, omega s by omega p is greater than 1. It is in the stop band. So Cn of x can be represented as cos h of n cos h inverse. So from this, if we derive, we can get back the n value. Then n is equal to n is greater than or equal to cos h inverse of square root of 10 power 0.1 alpha s minus 1 by square root of 10 power 0.1 alpha p minus 1 by cos h inverse of omega s by omega. So in Butterworth, the order formula is logarithm of square root of 10 power 0.1 alpha p minus 1 by 10 power 0.1 alpha p minus 1 by cos h inverse of. Instead of cos h inverse, we will get logarithm. Here it is cos h inverse because of the Chebyshev polynomial. So remaining all are as it is only. So if they give the transfer function specification, we have to find out the order. After finding the order, we want to find out the poles of the transfer function. So here the poles of the transfer function, the Chebyshev is equal to, so a cos pi k plus jb sin pi k. It it is on an ellipse. Previously, Butterworth filter poles are on the circle, so it is e power j pi k. But here it is an elliptical formula. A cos pi k plus jb sin pi k. So the complex poles we have to get. The poles are located on a ellipse shape. So now with this, the low pass filter design of Chebyshev and Butterworth is over. Now let's move on to designing for high pass, band pass and band stop filters. So if you see frequency transformation, so from low pass to high pass, the frequency transformation can be represented in Z domain substitution. We can use Z domain or we can use S domain also. In S domain, so omega is represented with omega c by S. When we want to convert it into high pass, low pass wants to be converted into high pass, S is replaced with 1 by S. But here it is omega c by S. Omega c at the beginning we will consider it as 1 radians per second. So that's why it is 1 by S. Right. So to convert it into low pass to band pass, we'll use some formulas for converting it into S domain. But actually, while performing this conversion operation, we'll perform in analog domain itself. We'll calculate H of S for low pass filter, and H of S low pass filter is converted into high pass filter by substituting suitable S value. And if it is for band pass filter, we'll convert H of S into low pass filter H of S into band pass filter H of S, and then it is converted into the digital by using some transformation techniques. So we have designed up to analog type only, low pass filter, and then low pass to another filters just by substituting S with suitable formula for frequency transformation. So we are not going to discuss about that frequency transformation, derivation and so on. Just the formulas we want to remember. For omega, S has to be replaced with omega c by S, so converted into high pass filter. So if it is for low pass, if it is for band pass filter, then it can be like S square plus omega u omega L by S into omega u minus omega. Some kind of upper cutoff frequency and the lower cutoff frequency are involved in the band pass filter and band stop filter. Now, now let us discuss about this frequency transformation is over. Next, we want to convert it into analog to digital transfer. So while converting analog to digital, we have some kind of transfer functions, some kind of techniques we want to use. So we have two types of techniques to convert analog transfer function to digital transfer function. So there are four types of techniques. Two are most familiar techniques. One is impulse invariance method. Another one is bilinear transfer. In impulse invariance method, we'll convert the analog transfer function into digital by using a partial fraction. So we have to convert the just let me clarify this one by using with a problem. Will complete it. So the first we have to find out h of s into sum of subtransfer functions. So the subtransfer functions are single order transfer functions. So h of s is equal to this is h of s is equal to, it represented as a sigma ck by s minus pk. So in impulse invariance method. So if you do impulse invariance method as a sum of single order subtransfer function, this can be directly converted into digital by substituting h of z is equal to sigma ck by 1 minus e power pkt into z inverse. So if you know pk, pole location in the analog domain, in the digital domain it is equal to e power pkt, because s is equal to e power sigma t is the formula for, or e power st. So z is equal to e power st is the formula for the relation between z domain and s domain. So z domain is for digital and s domain is for analog. When you are converting h of s into h of z, that means the low pass, sorry, the what we can say, the analog transfer function h of s is converted into digital. The digital is h of z. So the simple thing is we want to find out the transfer function in the form of partial fraction so that we can find the poles of the transfer function. So if you know the pole, directly we can find the h of z as 1 by 1 minus e power pk into t. T is some sampling interval delta. But the problem in this method is aliasing effect. The frequency is because we know the formula z is equal to e power st. S is equal to sigma plus j omega. So when omega is separated with 2 pi, then it is equal to e power s sigma plus j omega only. If it is sigma plus j omega plus 2 pi is also equal to sigma plus j omega. So hence it has aliasing. When we are converting analog transfer function to digital transfer function, when the frequencies are separated by 2 pi in analog, that can be mapped into one pole in the digital. The frequencies which are separated at a distance of 2 pi in analog frequency scale, that all are mapped into one pole in the z domain. So because there is no distinction, the difference between the pole locations which are separated by 2 pi distance in the frequency scale. So we will get only one pole in the digital. So that is called aliasing effect. High frequency components are mapped into low frequency components. So to avoid this drawback in the impulse invariance method, we'll move on to the bilinear transformation. In bilinear transformation method, we are not going to do partial fraction. Just we'll substitute s is equal to, that's what we are going to discuss. Bilinear transformation technique, s has to be substituted with 2 by t into 1 minus z inverse by 1 plus z inverse. So 1 by t is represented with frequency 2fs into 1 by z inverse by 1 plus z inverse. If you find h of s, in the h of s, s is substituted with this z formula, just will directly convert it into z domain. But the drawback here is pre-warping method. So pre-warping method means the relation between the analog frequency and digital frequency are a little bit non-linear in some portion of the frequencies. That non-linear frequency is called the wrapping, frequency wrapping. So this is the only drawback, but otherwise it is exactly mapping the poles one to one. If it is having 10 poles in the analog transfer function, it has distinct 10 poles in the digital transfer function. There is no aliasing in the bilinear transformation. Okay. So with this, the transformation of analog transfer function into digital transfer function is also same as like converting frequency translation. So low pass to high pass by substituting the formula into the H of S, we can convert low pass to high pass, and low pass to band pass, or low pass to band stop. But in the unlock to digital transfer function, we no need of converting S domain to S domain. Directly we are converting S domain to Z domain. So we have well-known methods are two: impulse invariance and bilinear. So let us see a problem on digital filter design. So if you see the digital filter design, so that we'll apply H of S, and then that is converted into digital by using some transformation technique, either impulse invariance method or bilinear. So let's check the problem with this. This is only conversion, but we want design problems also, and then we will convert into digital. So let's take this method and we'll glance on. For the given specification of alpha p equal to 3 dB, alpha s is equal to 16 dB, and rho is equal to 1 kilohertz, and fs is equal to fp, actually it is fp is equal to 1 kilohertz and fs is equal to 2 kilohertz. Determine the filter order and design analog low pass Chebyshev filter. So directly they mention analog filter we want to design. Analog filter means we want to calculate only H of S, only to calculate H of Z. So just let's shortlist the given specification. Alpha p is equal to 3 dB, alpha s is equal to 16 dB, directly they give. But omega p has not mentioned. What is the omega p for our problem? They have given 1 kilohertz. 1 kilohertz has to be converted into radians. 2 pi fp, f is equal to 1 kilohertz, so 2000 pi radians per second. Similarly, omega s is 4000 pi radians per second. So now everything is studied. It has alpha p and alpha s, omega p and omega s. Just will substitute n formula. For the Chebyshev, it is cos h inverse of square root of 10 power 0.1 alpha this minus 1 by square root of 10 power 0.1 alpha p by cos h inverse of omega s by omega p. Just if you substitute this alpha s, alpha p, omega s, omega p, we will get a transfer, we will get an n value. So here n is greater than or equal to 1.7533. We want to round off it to the next higher integer. So next higher integer is 2. Next we want to find out pole locations. What is pole location? As I told, it follows ellipse. So what is this ellipse is? It is in the shape of sigma plus j omega. Sigma plus j omega. What is sigma? Means a cos pi k. So what is omega? A b sin pi k. So this is a cos pi 1 plus j b sin pi 1. Pi 1 is nothing but simply pi k. It is, we will substitute. So what is a and b values are? So as I told, it is the pole locations are lies on a ellipse. So the a and b are nothing but major and minor axis length. So a b values are calculated from the well-known formulas. Is nothing but a is equal to omega p into mu power 1 by n minus mu power minus 1 by n by 2. So what is mu again? It is backtrace. So mu is equal to 1 by square root of 1 plus epsilon square by epsilon, and so we'll substitute the values. And before that, we want to know the specifications first, and we should able to calculate the n value and then frequency transfer function. Okay. So here we calculated n. Now omega p we know, and mu we want to calculate. Mu we will calculate like this, and we'll substitute a value, and in a we'll get some 911.95, and similarly we'll get pi b value some 2198 pi. So after finding this ab, just we want to substitute it is in a cos pi k plus jb sin pi k. So pi k also we know. So this is the formula for pi k. Just we will substitute k is equal to 0 to n minus 1 will pi k. So these poles can be calculated now. A cos pi k plus jb sin pi k. Just if we take k is equal to 0, this pi naught k equal to 1 means pi 1 sin pi 1 cos pi 1. So we'll substitute this A value here and B value, we'll calculate the transfer. So S, so two poles, so 1 by S minus P naught into S minus P1. So two poles are substituted and it is simplified. We get a higher order transfer function. So from this we can calculate the numerator value K, so which can be easily calculated by using with this the filter design, IIR filter design by using Chebyshev and Butterworth filters, and how we want to convert it into low pass to high pass, we have design. And then next we want to find out like analog filter transfer function. Thank you. So it's the overview of IIR filter. So you just go through the quizzes I given, and we have given the solutions for the quizzes with explanation, and study material also given. This handwritten materials are available. Just go through it and have a complete glance on the filters. If any queries, you can just post in the comment box. Thank you.